Good day, everyone. So, in this lecture, we will discuss an overview of the data mining process. We will give an overview of the steps involved in data mining, starting from a clear, good definition and ending with model deployment. The general steps are shown or are will be provided, and we also discuss issues related to data collection, cleaning, and pre-processing. We introduce the notion of data partitioning, where methods are trained on a set of training data and then their performance is evaluated on a separate set of validation data, as well as explain how this practice helps avoid overfitting. Finally, we illustrate the steps of model building by applying them to data. In the previous lecture, we saw some very general definition of data mining. In this lecture, we will introduce the variety of methods sometimes referred to as data mining. The core of this course focuses on what has come to be called predictive analytics, the tasks of classification and prediction, as well as pattern discovery, which have become key elements of a business analytics function in most large firms. Those terms are described and illustrated in the next slide. So we will not cover in this course to any great extent the two simpler database methods that are sometimes considered to be data mining techniques, which are first the OLAP or online analytical processing, and two SQL or structured query language. OLAP and SQL searches on databases are descriptive in nature and are based on business rules set by the user. Example, find all credit card customers in the certain zip code with annual charges greater than 20,000 who own their home and who pay the entire amount of their monthly bill at least 95% of the time. Although SQL queries are often used to obtain the data in data mining, they do not involve statistical modeling or automated algorithmic methods. The core ideas in data mining includes classification, prediction, association rules, predictive analytics, data reduction and dimension reduction, data exploration and visualization, supervised and unsupervised learning. A fundamental distinction among data mining techniques is between supervised and unsupervised methods. Supervised learning algorithms are those used in classification and prediction. We must have data available in which the value of the outcome of interest, or example, the purchase or no purchase, um, that is known. Such data are also called labeled data, since they contain the label or the outcome value for each record. This training data are the data from which the classification or prediction algorithm learns or is trained about the relationship between predictor variables and the outcome variable. Once the algorithm is learned from the training data, it is then applied to another sample of labeled data which are also called the validation data, where the outcome is known but initially hidden to see how well it does in comparison to other models. If many different models are being tried out, it is prudent to save a third sample, which also includes known outcomes, that, or this is called the test data, to use with the model finally selected to predict how well it will do. The model can then be used to classify or predict the outcome of interest in new cases where the outcome is unknown. Simple linear regression is an example of a supervised learning algorithm. Although rarely called that in the introductory statistics course where you probably first encountered it, the y variable is the known outcome variable and the x variable is a predictor variable. A regression line is drawn to minimize the sum of square deviations between the actual y values and the values predicted by this line. The regression line can now be used to predict y values for new values of x, for which we do not know the y value. Unsupervised learning algorithms are those used where there is no outcome variable to predict or classify. Hence, there is no learning from cases where such an outcome variable is known. Association rules, dimension reduction methods, and clustering techniques are all unsupervised learning methods. Supervised and unsupervised methods are sometimes used in conjunction. For example, unsupervised clustering methods are used to separate loan applicants into several risk level groups. Then, supervised algorithms are applied separately to each risk level group for predicting uh, propensity of loan default. Supervised learning requires good supervision. In some cases, the value of the outcome variable, or sometimes called the label, that is known because it is an inherent component of the data. Web logs will show whether a person clicked on a link or not. Bank records will show whether a loan was paid on time or not. In other cases, the value of the known outcome must be supplied by a human labeling process to accumulate enough data to train a model. Email must be labeled as spam or legitimate. Documents in legal discovery must be labeled as relevant or irrelevant. In either case, the data mining algorithm can be led astray if the quality of the supervision is poor. Jean Wingerton reported in the January 5, 2014, Washington Post magazine how the strange phrase defiantly recommend is making its way into English via autocorrection. Defiantly is closer to the common misspelling definitely than is definitely. So Google.com in the early days offered it as a correction when users typed the misspelled word definitely. In the ideal supervised learning model, humans guide the autocorrection process by rejecting defiantly and substituting definitely. Google's algorithm would then learn that this is the best first choice correction of definitely. The problem was that too many people were lazy just accepting the first correction that Google presented. All these acceptances then commented or cemented defiantly as the proper correction. An example of supervised learning method is classification. It is perhaps the most basic form of data analysis. The recipient of an offer can respond or not respond. An applicant for a loan can repay on time, repay late, or declare bankruptcy. A credit card transaction can be normal or fraud. A packet of data traveling on a network can be benign or threatening. A bus in a fleet can be available for service or unavailable. The victim of an illness can be recovered, be still be ill, or be deceased. A common talk in the data mining is to examine data where the classification is unknown or will occur in the future, with the goal of predicting what the classification is or will be. Similar data where the classification is known are used to develop rules, which are then applied to the data with the unknown classification. Prediction is similar to classification, except that we are trying to predict the value of a numerical variable, example, amount of purchase, rather than a class, example, purchaser or non purchaser. Of course, in classification, we are trying to predict a class, but the term prediction in this course refers to the prediction of the value of a continuous variable. Sometimes in the data mining literature, the terms estimation and regression are used to refer to the prediction of the value of a continuous variable, and prediction may be used for both continuous and categorical data. Association rules and recommendation systems. Large databases of customer transactions lend themselves not to, n- to the analysis of associations among items purchased or what goes with what. Association rules, or sometimes called affinity analysis, is designed to uh, find such general association patterns between items in large databases. The rules can then be used in a variety of ways. For example, grocery stores can use such information for product placement. They can use the rules for weekly promotional offers or for bundling products. Association rules derived from a hospital database on patient symptoms during consecutive hospitalization can help find which symptom is followed by what other symptom to help predict future symptoms for returning patients. Online recommendation systems, such as those used in Amazon.com and Netflix.com, use collaborative filtering, a method that uses individual users' preferences and tastes uh, given their historic purchase, rating, browsing, or any other measurable behavior indicative of preference, as well as other users' history. In contrast to association rules that generate rules general to an entire population, collaborative filtering generates what goes with what at the individual user level. Hence, collaborative filtering is used in many recommendation systems that aim to deliver personalized recommendations to users with a wide range of preferences. The performance of data mining algorithms is often improved when the number of variables is limited and when large numbers of records can be grouped into homogeneous groups. For example, rather than dealing with thousands of product types, an analyst might wish to group them into a smaller number of groups and build separate models for each group. On a marketer might want to classify customers into different personas uh, and must therefore group customers into homogeneous groups to define the personas. This process of consolidating a large number of records or cases into a smaller set is termed data reduction. Methods for reducing the number of cases are often called clustering. Reducing the number of variables is typically called dimension reduction. Dimension reduction is a common initial step before deploying data mining methods intended to improve predictive power, manageability, and interpretability. One of the earliest stages of engaging with a dataset is exploring it. Exploration is aimed at understanding the global landscape of the data and detecting unusual values. Exploration is used for data cleaning and manipulation, as well as for visual discovery and hypothesis generation. Methods for exploring data include looking at various data aggregations and summaries, both numerically and graphically. This includes looking at each variable separately as well as looking at relationships among variables. The purpose is to discover patterns and exceptions. Exploration by creating charts and dashboards is called data visualization or visual analytics. For numerical variables, we use histograms and box plots to learn about the distribution of their values to detect outliers, extreme observations, and to find other information that is relevant to the analysis task. Similarly, for categorical variables, we use bar charts. We can also look at scatter plots of pairs of numerical variables to learn about possible relationships, the type of relationship, and again to detect outliers. Visualization can be greatly enhanced by adding features such as a color and interactive navigation. So, in our course, we will focus on understanding and using data mining algorithms, which will be um, in the step 7 or step 4 to 7. However, some of the most serious errors in analytics projects result from a poor understanding of the problem, an understanding that must be developed before we get into the details of algorithms to be used. Here are the list of steps to be taken in a typical data mining effort. First, develop an understanding of the purpose of the data mining project. How will the stakeholder use the results? Who will be affected by the results? Will the analysis be a one shot effort or an ongoing procedure? Next step, is to obtain the dataset to be used in the analysis. This often involves sampling from a large database to capture records to be used in an analysis. How well this sample reflects the records of interest affects the ability of the data mining results to generalize to records outside of this sample. It may also involve pulling together data from different databases or sources. The databases could be internal, for example, past purchases made by customers, or external, example or the credit ratings. While data mining deals with very large databases, usually the analysis to be done requires only thousands or tens of thousands of records. Third step is to explore, clean, and pre-process the data. This step involves verifying that the data are in reasonable condition. How should missing data be handled? Are the values in a reasonable range given what you would expect for each variable? Are there obvious outliers? The data are reviewed graphically. For example, a matrix of scatter plots showing the relationship of each variable with every other variable. We also need to ensure consistency of in the definitions of fields, the units of measurement, time periods, and so on. In this step, new variables are also typically created from existing ones. For example, the duration variable can be computed from start and end dates. Next step, number 4, reduce the data dimension if necessary. Dimension reduction can involve operations such as eliminating unneeded variables, transforming variables, example, turning money spent into spent is greater than $100 versus spent is less than or equal to $100. And creating new variables. Example, a variable that records whether at least one of several products was purchased. Make sure that you know what each variable means and whether it is sensible to include it in the model. Next step, determine the data mining task. Examples are classification, prediction, clustering, etc. This involves translating the general question or problem of step 1 into a more specific data mining question. 6. Partition the data for specified tasks or for supervised tasks. If the task is supervised, example in classification or prediction, randomly partition the dataset into three parts: training, validation, and test datasets. Next step, choose the data mining technique to be used, either regression, neural nets, hierarchical clustering, etc. 8. Use algorithms to perform the task. This is typically an iterative process, trying multiple variants and often using multiple variants of the same algorithm, choosing different variables or settings within the algorithm. Where appropriate, feedback from the algorithm's performance on validation data is used to refine the settings. Next step, interpret the results of the algorithm. This involves making a choice as to the best algorithm to deploy, and where possible, testing the final choice on the test data. to get an idea as to how well it will perform. Recall that each algorithm may be tested on the validation data for tuning purposes. In this way, the validation data become a part of the fitting process and are likely to underestimate the error in the deployment of the model that is finally chosen. Next step, deploy the model. This step involves integrating the model into operational systems and running it on real records to produce decisions or actions. For example, the model might be applied to a purchase list of possible customers, and the action might be include in the mailing if the predicted amount of purchase is greater than $10. A key step here is scoring the new records or using the chosen model to predict the outcome value or the score for each new record. The foregoing steps encompass the steps in SEMA, a methodology developed by the software company SAS. Sample, explore, modify, model, assess. Sample means taking a sample from the dataset, partition into training, validation, and test datasets. Explore, examine the dataset statistically and graphically. Modify, transform the variables and impute missing values. Model, fit predictive models, example regression tree or neural network. Assess, compare the models using a validation dataset. IBM, the IBM SPSS modeler, previously SPSS Clementine, a similar method termed CRISP-DM or CRISP-DM, short for Cross-Industry Standard Process for Data Mining. All those frameworks include the same main steps involved in predictive modeling. Datasets are nearly always constructed and displayed so that variables are in columns and records are in rows. We will illustrate this with a sample dataset called the Roxbury. So, in West Roxbury, Boston, in 2014, there are 14 variables recorded for over 5,000 homes. 14 variables are the total value, tax, lot, square feet, year built, gross area, living area, floors, rooms, bedrooms, full bath, half bath, kitchen, fireplace, and remodel. There are 5,000 homes, but we show here just a sample of those homes. The spreadsheet is organized so that each row represents one home. The first home assessed value was 3,444. Its tax was 330. Its size was 9,965 square feet. It was built in 1880 and so on. In supervised learning situations, one of these variables will be the outcome variable, typically listed in the first or last column. In this case, it is a total value in the first column.